Hello, physics class, and welcome to problem set 34. I hope you're having a good day today as we begin our lesson. We're still working on specific heat this week, and today we're going to be tackling specific heat of copper. Just picturing taking a penny and melting it down. You can see the specific heat and melting point of copper as it compares to that of water. First of all, think about the specific heat of water, 4,186 joules, whereas with copper, it's 386 kilograms, joules per kilogram degree Celsius. Excuse me, my notes are a little bit off there. It should say joules per kilogram Celsius. And so just think about the difference between copper and water. Water has a specific heat that's 10 times greater than that of copper. But copper has a melting point that is 10 times greater than water. So just kind of compare those two as we think about that. So the first thing, what we want to do is we want to take, picture we have approximately 5 pounds of copper. And we want to turn that into like liquid. We want like a glass of copper. I don't know what you do with a glass of liquid copper. Maybe you could form it into one giant penny, but that's what we'll be working on today. So let's start by taking our specific heat of copper, which according to what we have here, you can also find it on the chart that I provided you with. It's 386 joules per kilogram Celsius degrees. And then we're going to use a little bit of unit analysis. Again, this is specific heat. And we're going to take our 2.35 kilograms of copper. And we're also going to take the change in degrees. Now, it starts out at 33 and it goes to 1,083 degrees Celsius. So the difference between that, because we want to actually find the change in degrees Celsius, is 1,083 minus 33 degrees equals 1,050 degrees Celsius is the change in degrees Celsius. So 1,050 degrees Celsius. And then I'm also going to take the heat of fusion of copper, which the heat of fusion of copper is 184,000 joules per kilogram Celsius. And that wasn't Silas, that was our little girl Lily. And just so you guys know, again, with the heat of fusion, I made a mistake and I put Celsius in there. There is no change in temperature because what's happening is, remember that Dominion modeling we had for phase change from a solid to a liquid. What happens is you take the copper and you raise the temperature, raise the temperature, raise the temperature. So that's your change in degrees Celsius. But then you have this flattening off where the melting occurs. There's no change in temperature of the copper as the melting occurs. So that's why there's no degrees Celsius on the bottom of your heat of fusion. All you're doing in this, with the heat of fusion, is you're changing the state of the copper from a solid to a liquid. So now that we've done our unit analysis, we can apply it to begin finding the amount of energy, the amount of heat energy that it takes in order to melt the copper. So we'll take the specific heat, 386, and we'll multiply it by the mass of 2.35, and we'll multiply it by the change in temperature of 1,050 degrees Celsius. Now, if you remember the difference, the ratio of Celsius to Fahrenheit is there's 1 degree Celsius to 1.8 degrees Fahrenheit, And so it's about double. So if you're thinking you're raising this 1,000 degrees Celsius, that's like 1,800 degrees Celsius. So this is almost 2,000 degrees Fahrenheit. Excuse me, 2,000 degrees Fahrenheit. You'd have to raise the temperature of this copper. And so the total number of joules is 952,455. Now just imagine if we turn that into calories and how many Snickers bars that would take in order to be able to change the temperature of this copper. Now we're going to do the same thing down at the bottom. We're going to cancel out our kilograms. That will leave our only unit as joules. And we'll have 184,000 times our mass of 2.35 kilograms. And so we get 432,400 joules. Can you just picture in your mind? Think about this. This is what it takes to change the temperature of the copper. This is the energy that 2,000 degrees Fahrenheit. And that's the energy it takes to just melt the copper. It's amazingly similar. I know that the melting is half of what it changed, but that's 2,000 degrees. So I just think about those, and those numbers baffle my mind. So I'll add the two numbers together to get our total joules, the total amount of energy needed in order to melt the copper. 1,384,855. However, I can't guarantee you that that's exactly what it would be because we only have two significant digits in the problem. So I'm going to say 1.4 times 10 to the 6th power joules. All right? So hopefully we'll be ready for that question as you face it for the first time tomorrow on your quiz. The next question we have is the period of light ray is 1.89 times 10 to the negative 15th. Find the frequency, find the wavelength of this ray in a particular medium if the medium has an index of refraction of 1.25. So these questions are some questions that you've really been facing since this whole social distancing is done. So this is the first time I've really got a chance to work on a problem like this with you in a video. So we haven't really got a chance to talk about it. Hopefully maybe you've watched a video like this or you've been able to keep up with my inks in explaining how this works. So we have a few formulas that are very, very, very important to us. N equals C over V. You've seen these for the last couple weeks. F equals 1 over T. And V equals F and lambda. I don't know if you've been able to follow me, but this crazy looking thing that we put down here in this formula, it's a Greek letter lambda. And kind of want to explain some of the different symbols we have. N stands for index of refraction. C stands for the speed of light in a vacuum. And the speed of light in a vacuum, which is pretty set. It's a constant rate. It's always going to be the same speed in a vacuum, and it's pretty close to that, the speed of light in air. And it's 3.00 times 10 to the 8th meters per second. If you ever watched a science video, they'll tell you that it takes about 8 seconds for light to get from the sun, or 8 minutes for light to get from the sun to planet Earth. And that's how fast it's traveling, just so you can think about how far we are away from the sun, and it still is able to give us all the energy that we have. Pretty amazing. V stands for velocity of light in a medium. So when light passes through some other medium, like if you've ever seen light pass through a prism or into water, why it sparkles, why it makes the different colors and all that type of stuff is because the speed of the light changes as it passes through a different medium. The angle changes. That's why prisms work the way they do. And it changes the speed of the light. And so that's why this is so important. F stands for frequency. And T stands for period. And lambda stands for wavelength. So if you could kind of picture these, one of the things that you'd like to do is I like to draw kind of a standard sine wave, because that's usually the shape of light. So when we talk about period, it's how often it repeats. So you can see that this wave repeats. Period is the interval at which it repeats, and wavelength measures the distance from crest to crest. So that's why some of those wavelengths that you've been getting in your homework are very, very, very small answers. And so hopefully that kind of makes sense with all the stuff that we've been working on here. So let's begin to tackle this problem. The first one it says is find the frequency. I have two formulas that have frequency in them, the second and third one in these particular formulas that we get given. But what we're given here is period. So which formula is going to be able to be used in this particular problem? You're right, the second one. And the second one says frequency is reciprocal of period. That's what 1 over means. So it means frequency and period are reciprocals of each other. And so what we'll do is we'll say that if we know the period, the frequency is going to be equal to 1 divided by 1.89 times 10 to the negative 15th. And believe it or not, I don't know that off the top of my head. So what I'm going to do is I'm going to take out my handy dandy calculator, and I'm going to plug this question right into my calculator. Hopefully you can give this a try at home also. See if you get the same answer that I do. But when I put it in my calculator, I get the frequency of this being 5.291. Let's see, that's in hertz because it's frequency. And so that would be, times 10 to the 14th power. So that would be our frequency. Then it says find the wavelength. So we want to find out how many meters that wavelength is from crest to crest on a light wave. If you're thinking what I'm thinking, the number should be very, 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 very small. It says find the wavelength of this ray in a particular medium if the medium has an index of refraction of 1.25. So what that's going to let us do is it's going to let us find the velocity, because we need velocity here. And you'll see velocities in the first and third equations. So we'll start off by using N equals C over V. So right here we're given N as 1.25. I told you at the beginning of this question that the speed of light in a vacuum is a constant, 3 times 10 to the 8th power meters per second. And that will allow us to calculate for the velocity of light in this particular medium. We don't know what the medium is, so we're going to have to calculate that. We'll cross multiply velocity, so we'll get 1.25 V equals 3 times 10 to the 8th. Then we'll take 3 times 10 to the 8th, and what we'll do is we will take 3 times 10 to the 8th, typing this into my calculator, and we're going to divide by the other side, divide by 1.25. So I get velocity of this is 2.4 times 10 to the 8th. Now that I have velocity, I can plug it into the third equation, which will allow me to find wavelength. So the third equation is velocity of light in a medium equals frequency times wavelength. And we already have learned in this lesson that the velocity is 2.4 times 10 to the 8th meters per second, and the frequency is 5.291 times 10 to the 14th times wavelength. So now, just by looking at that, like if I were to take out and say, I'm going to do a visual inspection of what's going on right here. If I take 8th power and divide it by the 6th power, I'm going to get a very, very, very small number. And that's what I'm supposed to be getting. So what I want to do is I want to do 2.4 times 10 to the 8th, and I want to divide that by 5.291 times 10 to the 14th equals the wavelength. So now I'm going to get out my calculator. Now this is where I want to be very, very, very careful. Don't just type what you see. And if you do, you will get the wrong answer. So I implore you, I beg you, please use parentheses for your own good, because parentheses are really, really, really going to be your friend in this particular problem. Okay? So what I did was I said 2.4 times 10 to the 8th. And I made sure that I got my value of 240 million on my calculator. I hit divide, open my parentheses, multiplied by 5.21 times, and I started another set of parentheses, 10 raised to the 14th, and I closed 2 sets of parentheses, ensuring that order of operations was done appropriately. And when I did that, I got 0.00000454. And I'm just kind of writing this down. Normally, if I was doing this, and you don't have to do this, I wouldn't write down all those zeros. I just do a little bit of scientific notation. I moved it 1, 2, 3, 4, 5, 6, 7 times, and I got 4.454 times 10 to the negative 7th meters is the wavelength of that light, which makes sense. You would think from crest to crest. I said times 10 to the negative 7th, but then I wrote to the 4th. Negative 7th power. Now, be very, think about this. If I was getting a huge number for that wavelength, I'd have to think to myself, that doesn't make much sense. So think about your answers. We'll apply our 3 significant digits here to my 2 questions. I got also the frequency was the first question, and I'm going to have 5.29 times 10 to the 14th hertz. All right, if you got any questions on that before the quiz tomorrow, let me know. Don't give me a call during the quiz. Call me before the quiz. Okay? All right, next question. Tom fired a gun into the air from a cliff of 71 meters. The bullet headed out at 75 degrees and with an initial velocity of 950 meters per second. How far did the bullet go, and what was the maximum height of the bullet? What was the speed of the bullet just before it hit the ground? And how long does everybody have to get out of the way? These particular questions, if you've been paying attention to them, they are very, very time consuming. There's a lot of work that goes into this. As I'm doing this on this video, you might find me doing a little bit of work that I normally would put down, but for space, it's not going to happen. So here's this guy. He's firing his gun into the air at 71 degrees. His initial velocity is 950 meters per second. We are asked the question, how far did the bullet go? So that means we want to find the change in x. It says what was the maximum height of the bullet. That means we want to find the height, the top that the bullet gets, and the final velocity in the horizontal direction. So the first question I want to tackle is how far it traveled. And in order to find out how far it traveled, we have to find the amount of time that it's in the air. And so what we're going to do is we're going to take vertical velocity, and that's what we're going to start with. Sorry, vertical position. Vertical position equation. So the position equation says that x final, actually because it's vertical, and I don't have to do this, the formula still stays the same, but just for everybody's sake, I'm going to put a y. Because x we'll use for left to right, y we'll use for up and down. So vertical position equals acceleration times time squared over 2 plus velocity initial times time plus position initial. Again, we're going to call it y just because we're talking about vertical up and down. So what's the final position of this bullet? We want to find out when it hits the ground, how far has it traveled horizontally? So the final position is going to be 0. What else does that tell you? I made a mistake in my diagram, and this degree is supposed to be 75 degrees, and the height of the cliff is 71 meters. All right, so now another thing that I know is that we are positive 71 meters off the ground. What's the vertical acceleration? Yeah, it's negative 4.905 t squared. And the velocity initial is actually, and I probably should have given myself a little bit more room over here. The velocity initial is 950 times the sine of 75 plus 71 meters up in the air. Oh, let's simplify things just a little bit. I'll take 950 sine 75. I typed it in wrong. 950 sine 75 gets 917.6295 t plus 71 negative 4.905 t squared equals 0. So now I have an a value, a b value, and a c value. So I can apply Pythagorean's theorem. Negative b, so negative 917.6295 plus or minus b squared, which is 917.6295 squared, minus 4 times a times 71, all over 2 times a. All right, now I'm going to begin to simplify a little bit. And just so you know, I'm only going to write down things that I absolutely need to write down for space on this particular problem, because I want these all to be on my inks. So I'm going to say, first thing I'm going to do is I'm going to do 917, and I'm going to square it. So I'm going to get 917.6295 plus or minus, and when I square it, I get 842,043.9 plus, and then I'm going to, just for kicks and giggles, I'm going to multiply 4 times 4.905 times 71. You've seen me do this in other times throughout the year. I've done this in its own separate step. But again, for time's sake, I'm going to do those together. All over 2 times 4.905 is going to give me negative 9.81. So then we'll add what's underneath the square root. So we'll get 1,093 plus 842,043.9635 gives me negative 917.6295 minus, and I'm going to just put the minus there. There's a reason I did that. 84346.98 all over negative 9.8. The reason is that I've got to have a positive answer at the end. There's two possibilities. I'm going to have a negative and a positive solution. I want to go with the positive one, and the only way to ensure that I get a positive one is if I have a negative divide by negative. So that's why I chose the negative solution in this particular case, because if I chose the positive one, that'd be going in the opposite direction. I get a negative time, and we don't want to go back in time. Not big into time travel. So we get negative 917.6295 minus 918.388 over negative 9.81. So now I'm going to take 918 plus 917.629, add those together, divide by 9.81, and we'll get time is equaling 187.15. That's a long, long time to be in the air. Remember we were learning about falling body problems earlier this year, and so take that into consideration as we play this out. So next thing it says is how far does the bullet travel? That means we have to put this into back into horizontal position equation. And so we're going to have x final equals acceleration times time squared over 2 plus velocity initial times time plus position initial. This is a little bit easier because our acceleration in the horizontal direction is 0. It's not accelerating horizontally, just vertically. And the only thing accelerating it is gravity. Our initial velocity in the horizontal direction is 950 cosine 71, and our initial and times the time, which was 187.1577. So that was the time, and then plus the initial position, which was 0. We don't have any reference horizontally. So basically we've got to take our 187 and multiply it by 950 times the cosine of 71. And because order of operations says I can do all those together in one step, I will, no problem. So x final equals, I'm looking here at just checking things out, 57,885.96 meters. I look back in the problem, I find two significant digits, so we x final equals 58,000 meters. It would be really, really, really terrible is if your teacher put in multiple types of units into this. Thank the Lord, your teacher chose not to do that in this particular case. What a nice teacher. What a nice, nice teacher. All right, so the next thing, that's only part A. I don't know if I'm going to have room enough to get to part C, but the next thing it asks for is what was the maximum height. So if we go to max height, what do you know about the maximum height? We've talked about this many times this year. That's that we have to apply the motion equation, which says velocity final equals acceleration times time plus velocity initial. And that final velocity at the maximum height is 0. That's when it's not going positively, a positive speed up in the air or a negative speed back down into the ground. All right, so our acceleration of gravity is 9.81, and our velocity initial was 950 sine 75. I got that from over here. Useful piece of information as being times time plus 917.6295. All right. So now we'll add 9.81 to the other side. 9.81t equals 917.6295. You could probably get pretty good at estimating the solution right there. So you can kind of check your work by doing estimating 900 divided by 9. It'd be approximately 100. I got t equals 93.54 seconds. Use common sense here. If the time total was 187 and about half the trip to get to its maximum height is about 93, except for you got to figure in it has to go 71 more meters on the way down. This all makes sense. But now I want to find the max height, so we're going to plug this back into the vertical position equation, which I had just a bit ago, as being position final in the y direction equals negative 4.905 times 93. I'm just abbreviating that for lack of, I'm going to put 93.54 in when I do it, plus, and the initial velocity we grabbed from right here as being 917.6295 times our 93. Oh, and that first one was supposed to be squared. Plus, whoops, excuse me. Got a little too far to close to the edge of the screen. Plus the 71 that we began with. All right. So we're going to take our 93 first, and we're going to square it. And after I square it, for space sake, I'm going to multiply it by 4.905. So I get y final equals negative 42,917.6. And then I'm going to do 917.6295 plus 93.54 times. I almost made a crucial error to get 85,835 plus 71. So I'll just start adding this. What I got, add 71. And then when I take that, I'll subtract 42,917.6 to get a maximum height of 42,988 meters. Apply my two significant digits. I'm going to get my maximum height as being approximately 43,000 feet. So far I've gotten two answers, 58,000 meters in the horizontal, 43,000 meters in the vertical. Okay, and a lot of that has to do with the pull down of gravity. Why? Because you might think, well, he had it angled up. Why is it going farther out if he had it angled up? Shouldn't it be going up more? Well, that's because gravity is constantly pulling that bullet down. And the last one, how far or how fast is the bullet going? What's the speed of the bullet just before it hits the ground? Let's use the motion equation one more time, and let's talk about the velocity in the y direction as it falls. So negative 9, and we're going to find it in the y direction, negative 9.81. And the time it was in the air, the total time in the air, we decided was 187.1577 plus our velocity speed in the vertical direction, which we've decided a few times was 917.6295. Got that from right there. Okay, so now we'll take our 187. And by the way, I got this 187 number for total time right there. And I'm just plugging it into the motion equation. 187.1577 times 9.81 gravity gives me negative 1836.017 plus 917.6295. So we get velocity final in the y direction equals negative 918, or two significant digits, negative 920 meters per second. So speed just before it hit the ground, everybody has time of 100, and we got to say they got 180 seconds to get out of the way, because if they wait till, that's kind of a greatest integer question, because if they waited to 190 seconds, they're too long. So think back to your lessons in math class about greatest integers. If they waited 190, they're in trouble. They're too late. You can't round up on that last question, and so you'll have to say 180 seconds. Hope that's making sense to you. I think I got one more problem to work on today, and that is a rectangular tube is placed in water. This is another buoyancy question, and so what we want to do with this particular buoyancy question is, let's start with what we know. And we know the density of water is 1,000 kilograms per meter cubed is the density of water, and we want to find the volume of the block, which is going to be found by length times width times height. And we also want to find the volume of the block that is submerged under water. Okay, so let's provide ourselves with a free body diagram. We'll start by giving ourselves a body of water, and then let's put a nice rectangular block. Eventually, and I think I've got this in here before the end of the year, and we're getting close to the end of the year, we're going to turn this into a boat. We got a block that's floating partially above the water. All right, and it says that the dimensions of the boat are 17 long, 9.75 wide, and a total of 13.24 high. But then it says 6.43 remains above the water. So 6.43 is above. So how much of it's submerged? How much of it's below the water? Well, we'll take our 3.2414 and subtract the 6.43 to get that 6.8114 is below the surface of the water. Does that make sense? So you got 6.4 above and 6.8 below as we're working on this problem. So what I want to start out with is finding the total volume of the block. So we'll find the total volume of the block by length, which we decided was 17, width 9.75, and the height is 13.2414. So we'll multiply those together. 17 times 9.75 times 13.2414 gives us volume of the block as 2,194.76 meters cubed. All right. Then the next thing I want to do is I want to find the volume of the block that's submerged. So in order to do the volume submerged, we're going to do the length of the block, again 17, 9.75 wide still, but this time we're going to use 6.8114 because that's the amount of the block that's underneath the surface of the water. So we're going to do 17 times 9.75 times 6.8114. So the volume submerged is equal to 1128.98955 meters cubed. Okay, so now what we want to do is we want to start by you applying Archimedes' principle. I've written this on so many slides up until this point. I hope you've seen them before. But it says, well, hello, why can't I get to the point where I can change my color? There we go. So we got Archimedes' principle states that the weight of the water displaced equals the buoyant force. So what we want to do is we would like to start with our density of water, 1,000 kilograms per meter cubed, and we are going to take the value of the submerged block because we want to find just the water that it's moving out of the way. So the submerged block's mass or volume is 1,128.98955 meters cubed, and that's the volume submerged, and this is the density of water. But then that's not going to give us buoyant force or weight of the water, either one. We got to turn that into newtons, so it's 9.81 newtons per every 1 kilogram. Now my kilograms are gone, my meters cubed are gone, and the only unit left is newtons. So we'll take 9.81 times 1,000 times 1128.98955 gives me a value of the force buoyant equals 11075,387. So we got 11 million newtons of force. That's the force pushing up on that block that it's holding up. Okay, now what we're asked to do is to turn this into the density of the whole block. So now it's floating. Remember that? We stated at the beginning that this was floating, and if that's floating, that means that in the end it has to have a density less than water. So let's start with our buoyant force, 11,075. 387, and let's just do a little bit more unit analysis to get back to, and that's in newtons. So now we're going to take 9.81 newtons per kilogram. I hope you notice that I could have left the newtons out at the beginning and here, and I'd still get the same, but you need to understand that so you can understand the buoyant force. But in the practicality, if you were able to skip that step, you could in these particular problems. But now I got the newtons are gone, I got kilograms, so there's one more thing I need meters cubed on the bottom. So I'm going to put down my the total block, 2,194.76 meters cubed. That's the volume of the total block, and this is gravity, and this is the force buoyant. Okay, so now we'll take our value, 11 million, divide by 9.81, and then we're going to divide by the volume of the block, 2,194.76, to get the density of the block. Again, less than water. I got 3 significant digits, 514 kilograms per meter cubed. And that right there is the solution. So I hope that you're getting these problems. There will be a quiz, problem set 34, tomorrow. Just so you know, we're going to do problem set 35 next week, and then the rest of the class will be preparation for your final exam. I know this is going to be strange. It's going to be a strange time, And if you've got questions, if you got anything you need, give me a call. I can talk to you guys somehow through Zoom or Google Duo if you need to do face to face, or just let me know. We'll be working on this, and I will talk to you later. Have a great day.